Thus far, all the examples we have looked at deal with chance in what we may call discrete spaces or discrete settings. The word discrete that we use here stands for finite or countably infinite. If you cast your eyes back, metaphorically speaking, to the particular problems we've looked at, you'll recognize that every one of the problems has outcomes which one could enumerate. The outcomes were either finite in number or could be enumerated sequentially in principle were there world enough and time. For example, by counting them out a la the natural numbers or the integers. Now, this is the setting that we've looked at there so far, and therefore this provides a useful test setting in which we can test out our assumptions, our axioms, and see whether we can construct probability measures in consonance with the axioms. So let us begin. The first example we looked at dated back to the awakening in 17th century Europe in the glittering salons running from Paris through Vienna to Prague. And we posited as our first problem the problem posed by Chevalier de Marais, and here is one of the two problems that he posed. Suppose a die is thrown 4 times. What are the chances that no ace is seen? Now let's pause and summarize our discoveries in the light of the nomenclature, the terminology that we've built up. First, what are the idealized outcomes of this chance experiment? What is the sample space? Now, it is natural in this setting to identify the outcomes of the die throws one at a time. The first throw, the second throw, the third throw, the fourth throw. In this sense, as far as the collected outcomes are concerned, the experiment is indistinguishable from throwing 4 distinct dice, let's say 4 different colored dice, at the same time. Time is not of the essence at this point. Now, if one does this, then we simply label the outcomes, outcome by outcome for each of the 4 dice, and we then end up as an idealized outcome for the overall experiment, a 4-tuple of integers. Naturally, we'll give the integers names, say k1 for the first die, k2 for the second, k3 for the third, and k4 for the fourth. And this ordered 4-tuple of integers, where each integer runs between 1 through 6, form all possible conceivable outcomes of this experiment. Now, the natural description here is in terms of 4 tuples of integers, but in principle there are a finite number of possible outcomes, in fact exactly 6 to the power 4 outcomes, 1296 such 4 tuples. And we could, in principle, have just labeled them 1, 2, 3, 4, 5, all the way up to 1296. Of course, then, this would rely upon us having a dictionary of translation, where for each 4-tuple, we then assign a number. A rose by any other name would smell as sweet in this context. It makes little matter what we call an outcome, as long as we can identify it. Now, having got this collection of outcomes, what are the events of interest here? Well, in this case, the event is, let us say A, that no ace is seen. Identify the word ace in this context with throwing a 6 in a die. Now, if no ace is seen, then none of your 4 die throws could result in an ace. And therefore, A corresponds to the particular subset of 4 tuples where none of the elements k1, k2, k3, or k4 can be 6. In other words, k1, k2, k3, and k4 have to represent numbers from 1 through 5. There are exactly 5 to the power 4 or 625 different idealized outcomes in this particular subset. Finally, we come to the idea of a measure of chance. The probability measure here builds in two stages. First, we identify this experiment as one of a generic class of Earn models, where every idealized outcome or sample point is equally likely. What does it mean? Well, there are 6 to the power 4 possible sample points in the sample space, 1,296 sample points, and therefore, to that event consisting of a singleton sample point. Now, what does that mean? It is a set consisting of one outcome alone. Let's say the outcome we pick consists of the integers k1, k2, k3, and k4. Notice the nomenclature, the terminology. We put curly brackets around a single outcome to distinguish it from an outcome. This is a set consisting of one outcome. This kind of distinction seems like just shuffling words around, but it is important. You see, probability measure can assign values to sets, not to sample points. And therefore, we identify the singleton sample point consisting of one element. And to each such singleton sample point, we allocate the value 1 over 1,296. This is how we begin. To borrow the language from physics, we will think of singleton sample points as atoms of this experiment. Now, we've allocated equal mass in this terminology, in this language, to the atoms. Now, we build upon this by looking at the event A, which consists of 625 different atoms, and allocating to A the sum of the atomic probabilities for each of the atoms. Of course, in this case, it is very, very, very simple, because each of the atoms has got the same probability, 1 over 6 to the power 4, 1 over 1,296. There are exactly 625 different elements in A, and therefore the probability of A is the cardinality of A, 625, divided by the cardinality of omega, 1,296. Now, this is the setting of Earn models, where all outcomes are equally likely. How do we proceed if we move on to a setting where the outcomes are not equally likely? Well, we considered the first throw in the game of craps. Recall, in craps, we repeatedly throw a pair of dice, and in the first throw, we've thrown 2 dice, and we simply sum the face values. The question: what is the chance of losing on that first throw in this game? What is the sample space? Well, as long as we're considering just the first throw, we're summing the face values of 2 dice, and therefore the numbers that we'll obtain are between 2 and 12. The sample space consists of exactly 11 points, the integers 2 through 12. Excellent. What is the event of interest here? Well, the rules of craps say that you lose on the first throw if you happen to throw a 2 or a 3 or a 12. This then is the event A of interest. It consists of that particular subset of these 3 sample points, 2, 3, and 12. How does one assign a probability measure to this experiment? Again, we begin one atom at a time. Elementary considerations lead us to assign to the atom consisting of the set with just the element 2 in it, the probability 1 in 36. And likewise for the atom consisting of the element 12. For 3 and 11, we assign a chance of 2 in 36. For 4 and 10, we assign a chance of 3 in 36, and so forth. Now, we now have a system of atomic probabilities. How do we compute the probability of A? Well, we identify that A is comprised of 3 atoms, 2, 3, and 12, and we simply sum the atomic probabilities to get the probability of A. Now, how does one go beyond this? Well, the next experiment we considered was when we had not just a finite number of outcomes, but a denumerably infinite number of outcomes. And so we returned to the tossing of a coin. The experiment in context was the following. Toss a coin repeatedly until the same face shows twice. Then stop. What are the chances that in this experiment one has to toss the coin 4 or more times? Well, let us begin with a sample space. Now, of course, this is an infinite sample space, so we can't enumerate all of them, but we can deduce what the pattern is. For example, a sample point could consist of 2 heads or 2 tails, or as we have seen, a tail and 2 heads, or a head and 2 tails, or a head, a tail, and 2 heads, or a tail and a head and 2 tails, and so on. And now the pattern becomes clear. A sample point has got alternating heads and tails and terminates with 2 of the same face. Now, before we go on, this looks like a messy description of the sample space, but we realize we could actually enumerate it. And in this case, one possible enumeration is to identify, to rename the sample point consisting of 2 heads and call it just 1. Rename the sample point consisting of 2 tails, call it -1. A tail, a head, and a head, call it 2, -2, 3, -3, and so forth. And it becomes clear that if one takes away the particular structure and language, the color of the coin-tossing experiment, that this is an instance where the sample space may be identified with a set of integers. Of course, there is an assumption here that one establishes a dictionary of translation ahead of time. So that if I say the integer 3, then it is clear to all parties involved that 3 stands for the outcome, a head, a tail, followed by 2 heads. But once the dictionary of translation is established, then the sample space is just the collection of integers. Now, in this space, what is the event of interest? The coin is tossed 4 or more times. Well, let's write this event in terms of our identification of the sample space as a set of integers. By looking at the table, it's clear that 4 or more tosses correspond precisely to the integers 3 or -3, 4 or -4, 5 or -5 ad infinitum. And therefore, we can, in a very compact sense, write down the event A of interest, that 4 or more tosses are required, as the collection of integers k, which in absolute value is at least 3. Oh, this is nice and simple. At least it's a compact description of what was a rather verbose, a colorful coin-tossing description of this problem. But of course, this presumes that there is an underlying dictionary of translation. Finally, how does one allocate a probability measure in this setting? Now, this is clearly not an EARN model anymore. This is a more complex model. But we've argued from first principles that it is natural to allocate to each atom probabilities which decay exponentially in powers of 2. Thus, the sample point 1, forming the atom consisting of just 1 as the sample point, has probability 1 in 4, as does the atom consisting of just the outcome 2 tails. 2 heads, 2 tails have labels k being 1 or -1. And therefore, we can identify with these particular atoms an exponentially decreasing probability. Now, one does this. Right? We have a systematic assignment of probabilities. 1/4 and 1/4, 1/8 and 1/8, 1/16 and 1/16, and so forth. How does one evaluate a probability? Well, A consists of all integers 3 or larger. To A, we assign the probability, which is the sum of the atomic probabilities, sum of these reciprocal powers of 2. And when we do this, we obtain, as we saw here, the probability 1 in 4. We should now use this to come up with an idea of how one builds chance models in discrete settings. This is next.